This video is going to go through the characteristics of capacitors that are in a series circuit. At this point, we've already done some circuit analysis. Now we're going to see how it all kind of connects and learn some laws of physics along the way. To begin with, I've got three circuits here. What I want to know is how is the potential difference across capacitors in series determined? So this is for you to do. Come up with a rule that can describe that. Pause the video and see if you can come up with your rule. So at this point, you've paused the video and you've thought about your rule. And when I look at this, I see my first rule as being, in series, the sum of the potential differences of each capacitor equals the potential difference across the whole series. This is actually conservation of energy, the law of conservation of energy. So if I look at the top circuit, I can see it starts at 12 volts and then it goes to 0 volts. That's our modern day symbol for ground. So it's 12 volts of energy, essentially, comes into it. Now remember, the potential difference is just proportional to the energy. So say 12 units of energy. And the first capacitor uses up 8 units, and the second capacitor uses up 4. It's conservation of energy. I'm given 12 to start with, and I use up all 12. In the next circuit, I start with 60, and I go to 20. That's 40 units of energy. And in my capacitor, I can see that I have 30 units used up on the left by the 5 microfarads, and 10 units used up by the 15 microfarads. Conservation of energy. For the bottom circuit, it's 232 volts and 100 volts. So that's a difference of 132, and sure enough, as I go through the circuit, 72, 24, and 36 is 132 volts, conservation of energy. Now there's a second rule. It's not quite so obvious, but let's show how it's derived. Let's start with the simple circuit. I've got a little piece of a circuit with the voltage on the left of VA, voltage on the right VB, and I've got two capacitors, C1 and C2, with potential differences of V1 and V2. The voltage, we're going to call that to be VA minus VB. So it's the difference of the two ends of the circuit. So what I know from our previous rule is that the total voltage, the difference between A and B, is equal to V1 plus V2. Well, I can describe voltage in terms of the capacitance as Q over C. So Q1 over C1 plus Q2 over C2. That's the two voltages. And I know that in series, all the charges are the same. So it's a property that we discussed when we were analyzing the circuits. So all the Q's are the same. So I don't need the subscripts anymore. I can just say that the voltage is equal to Q over C1 is equal to Q over C2. See, the second line's got a V1 subscript. That should be removed, but I don't have the ability to do it right now. So let's see, let's continue. I'll pull the Q out using the distributive property. So the voltage is equal to Q times the quantity 1 over C1 plus 1 over C2. Now I can also rearrange add my two numbers, finding a common denominator. So C1 plus C2 on the top and C1 times C2 on the bottom. But I'm going to do one more substitution, and I'm going to substitute for one of the capacitors. I'm going to pick C1. I could have picked C2. I'm just going to pick one of them. So I'll choose C1. I know that the charge on the capacitor is expressed as C1 times V1, so I'm going to replace the charge on C1 as C1 times V1 times the quantity in parentheses. That's great. That means that the C1s will divide out. So both C1s are now gone. So the voltage across the combination is equal to V1 times the quantity C1 plus C2 over C2. Remember what that C1 divided out. But I'm looking for the voltage at C1. So let me just rearrange this and put this expression on the other side. So when I move it to the other side, you can see that I got the voltage on V1, the potential difference, is equal to the voltage across the combination times C2 on the top divided by C1 plus C2. That's my new rule. So in my circuits, the potential is the fraction of the potential difference, where C1 is equal to the change in voltage across the combination times C2 over C1 plus C2. And if I look for C2, it'd be the change in voltage over the combination in times parentheses C1 divided by C1 plus C2. You can see in the numerator that whichever capacitor I'm looking at, I use the other capacitor's value in the calculation. Pretty handy. We can use these two rules to figure out a lot of problems without having to go through quite as much math. So, our law of conservation of energy combined with our second rule. Something interesting happens in this, though, is just kind of a trend. You can see the smaller capacitor has the higher or the larger potential difference. And you can see that in our numbers up there as well. So if I wanted to look at this circuit, I can see my 8 and my 4, but here's where they came from. I took my 12 volts and then multiplied it by rule number 2 to get 8 volts. The same thing for the 6 microfarad capacitor to get my 4 volts. Notice that whatever capacitor I'm looking at, so I'm looking at, say, the 3 microfarads on the left, in the formula I put the 6 microfarads. I don't put the 3 in, I put the 6. And I do the opposite on the other side for the other capacitor. Now let's look at a different circuit, the middle circuit. It's the same idea. The difference is going to be 40 volts between the series combination, and I did the same kind of combination, same kind of process using the 40s for my initial voltage. And that's where I got my values for 30 and 10 originally. Now the cool thing is I could have found the 30 and then just said the next one is going to be the total voltage across them, 40 minus 30, and that would leave me with 10. So I could use my second rule after doing this rule, combination of the rules. Here's the third circuit. I'll leave it for you to kind of look at what's gone on up here. So let's put the rules to the test by determining the unknown voltages or coming up with an expression that can be used to determine the unknown voltage. So I've got 22 volts on the top circuit, 10 on the right, 30 microfarads and 6 microfarads. I need to try to figure out what the voltage, the potential differences are going to be across the capacitors. So I'll pause here and leave this up to you to try to figure out. Okay, so hopefully you're unpausing and you can see what's going on. What I'm going to do is for the first one, I know I got arrows all over the place, but let's start looking at the 30 microfarads. At the 30 microfarads, I can use my rule 2 to calculate how much potential difference is used up by how much potential, let's just say, is used up across the 30 microfarad capacitor, and that's 2 volts. And then I can use rule 2. And rule 2 says the difference in these two ends of this series are going to be 12 volts. Then I subtract out the 2 volts, and that leaves me 10. So 10 volts is used up on the second capacitor. Now for the bottom circuit, this one's a little bit more straightforward. I start with 140 volts on the left, and it's going to go to 0 on the right. So I can just look at this as 140 minus 80 minus 20, and that's going to equal 40 volts. So the final one is going to be 40 volts. What's the charge on the unknown capacitor? I'll pause here and let you figure out. We haven't talked about this, but these are some of our older rules. Okay, now we're unpause, and one of the rules that we had before was that in series, the charge is the same for all the capacitors that are in that series combination. So in this case, what I could do is I could find the charge on any one of the capacitors I had enough information about, like the first cap, and I get 160 microfarads. Because they're all in series, that means each of these capacitors also has 160. So the 8 microfarads is 160 microcoulombs, and the unknown capacitor is also 160 microcoulombs.